We have very exciting panelists here. You saw the introduction. I don't need to go through all the introductions. I guess the format is each of us have a couple of minutes to talk about the slides, and then there are questions, and later we can open to the audience and get your feedback, inputs, questions, and comments. So let me start with my slide, and then I pass it along to our panelists. As you heard in the previous talk, the semiconductor industry has been one of the phenomenal examples of the innovation over the last few decades. And Moore's Law definitely is one of the drivers of this innovation path, but not necessarily the only one. And I'm going to talk about that a little bit later. But in general, semiconductor and innovation in solid state has been a cornerstone of the technology and technical innovation in our lifetime. And as Andy mentioned, sometimes you see that even Silicon Valley doesn't entertain silicon as much as it used to be, and it's all about apps and about the new opportunities on the network, which is very exciting. But what I wanted to highlight here is that unless we have this innovation in semiconductor industry going even faster than what Moore's Law offers, we are going to get to the point that all the new applications and exciting network-related or cloud-related applications are going to get to the point that we can't have enough hardware on the server side or the mobile side to facilitate or accommodate all those applications. So the big question is innovation in semiconductors slowing down? And there are reasons to ask this question. One is that, as you saw, Moore's Law is continuing, but it's getting slower. I mean, it takes a lot longer from the first sample to a lot longer and a lot more expensive from first sample to the point that you have a commercially available technology, plus the fact that it's very expensive and very few markets can address such a big volume potentials with 12-inch wafers and sub-28 nanometer technology. So that's why VCs are not funding semiconductor startups. And we know that one of the basic fields of innovation in the Valley and worldwide has been a startup. So are we getting to the point that we don't get enough innovation there? And if it's so, what's going to be the impact on the rest of the applications and technologies? So who is going to afford 640 terabits per second of IP data transfer over the network? Every second on internet, we have so much data going back and forth. And believe me, it's going through a lot of digital and analog silicons to get to that kind of like high speed. Or who is going to afford having 2x number of mobile devices? 2x number meaning that twice as many people you have in the world are going to be mobile devices. And it's just the mobile devices. And as you heard, there are even devices that are machine-to-machine connection. And these devices need to be running at extremely low power and highly efficient and link up with the cloud. So we see this potential for opportunities in innovation, but at the same time concerns that are we spending enough time? Because innovation in semiconductor takes a lot of physics and chemistry and electrical engineering and all of these things and a lot of investment to get to the next point. So the good thing is there's a lot of smart people still working in this technology. There are new devices that are going expediting in some cases or prolonging Moore's Law. We can see 3D structures coming up. So it's not just about how many transistors per millimeter square, but it's about how we can stack them up. Could be, of course, the extreme of that is packaging, but these technologies like FinFET or nanowire or even beyond CMOS, spintronics technologies are the ones that, again, can prolong this opportunity for scaling and for denser technologies. Also, we see that in many cases, of course, we can take advantage of Moore's Law, but it's not the only tool in our toolbox. For example, in many analog circuits, and by the way, the fastest growing market in semiconductor for the last few years has been analog, we don't benefit from the latest, finest geometry in technology. In fact, In many cases, we stick to technologies that are few generations behind a typical CPU because you need to power up those CPUs, you need to efficiently run them, you need to have a good standby. And by the way, the world that we are living in is analog world. What you are hearing is analog, what you are seeing is analog, and what you are feeling is analog. So you need to relate, no matter how strong your CPU is, you need to relate to real world, and that's where the interface to the world is going to be important. And we see that a lot of technologies, which is in complementary to Moore's law, is dealing with sensors, biosensors. We see that there is tremendous research and opportunities, which we can later talk about, and of course high voltage, because the smart grid story is not just about data transfer, but replacing some of these old switches with solid state switches, which brings another set of opportunities. And new applications. Of course, big data is a very popular name. I mean, and it's definitely an opportunity for a lot of innovations. But it's not just about assuming that all the information is now available on a disk and we need to run analytics on that one, but also we need to understand how to acquire data, how to digitize it, how to pass it around, and interfaces. Think of having data, the interfaces on chip, which is now in giga and potentially in the future terabytes. These are like very difficult problems, which is not just the scaling that solves it. It takes a lot of more innovation and innovative approaches in design. So sensor networks, smart grids are examples of that. During discussion, we are going to have specific topics related to these markets, which requires more innovation, and we need to address the issue of how we drive this innovation with understanding that VC community is not that favorable to semiconductor. So
when I was preparing for this, I wanted to think of a technology I could present that was truly disruptive. And when I start to think about, well, what is truly disruptive, I like to think about things that are going to involve people, a lot more people than are currently involved today, perhaps. I also like to think, especially in today's green environment, I like to think about efficiency. Can we do something with fewer programmers, more junior programmers? Can we do something with less power and effort than we did before? And thirdly, I wanted to have something that was going to have a broad impact, not just in a very small segment of market or a very small geography, that could be used worldwide. That could be used in everything from the smallest sensors or mobility devices all the way up through mega data centers, big compute systems, et cetera. Also knowing, and because Bashir invited me late, and I got to see a few of the different fields that were going to be presented, I knew we were going to have a fair number of software folks, and I also knew that we were going to have a fair number of folks talking about materials, talking about basic properties of semiconductors. So I tried to aim right down the center and wanted to talk a little bit about computer architecture today. And then the thing that came to me most to mind were APUs and HSA. APUs are accelerated processing units. And the best way to think of these is you can have two or more different distinct types of major compute units on the same die or on the same chip. For instance, today, AMD already has, as part of our APU processor line, a large CPU and a GPU on the same die. And you say, well, that's great, so that's one way to think of it, but how does that improve things from before? On top of that, or in conjunction with that, one could say we also have HSA, or heterogeneous system architecture. And this is the framework which enables a programmer or a set of programmers to move elements of work between the different compute units on that chip or on that die. And there's actually a foundation. This isn't an AMD alone thing. There's a foundation there. You can see the URL, hsafoundation.com. AMD's in it. A lot of folks here are TI, Qualcomm. I found out Broadcom was in earlier, Marvell, and a variety of others. And this is a large consortium that's going on industry-wide to say, hey, with heterogeneous computing, namely having two different types of major compute units, or two or more, on the same chip, what can we do with that? And how can we use that to move things forward? And I believe it was Joe that asked the question to Andy and the speaker, well, we've got all these cores, but what are we going to do with them? And that's a very hard problem. I think Andy said we might be up to like 1,000 cores and things in a few years. If you look at large data centers and things today, and you look at typically the chips and things that we have with multiple cores, and you actually look at the utilization on those cores, unless folks have spent a lot of money and a lot of time and a lot of very experienced program resource on this, only a small fraction of them are utilized at any time. What HSA enables you to do is really bring parallel programming to the masses. The HSA framework, in conjunction with heterogeneous systems such as APUs, enables work to be moved seamlessly and from the user's perspective, transparently between the different compute units. So more specifically, in terms of expanding programming to the masses, it's going to enable more efficient parallel programming. It's going to reduce over time the power that's used. In some cases, in examples we've seen, up to 25 times less power. And also provides benefits in markets. It's not just a large mega data center thing. You could also use it all the way down, from mega data center to, and HPC systems to big data, big compute, down through desktop systems, laptops, into tablets and mobile phones and things, et cetera.
All right, so good afternoon. My name is Piruz Parvarande. I'll wait for my slides to show up. So I'll provide you with an industry perspective from an analog mixed signal perspective. I think the things that we can all agree on is that within the semiconductor industry, there has been and continues to be a lot of consolidation. There are smaller companies that are being absorbed into larger companies, and the small companies, some of them are going out of business. We heard how VC funding is limited, and for the economic reasons that were articulated primarily in cases where you really need to rely on very deep submicron and very advanced technologies in order to bring your products out. The other trend that I see over the last 30 years that I've been in the industry is that the talent pool that used to be applied to the analog mixed signal community has been on a steady decline. And you can see that in the universities and the various mixed signal IC classes. The professors that I talk to seem to have difficulty finding funding for their work. And also there's a lot more attractive areas for these bright engineers, bright people to go to. They go into the software domain, they go to the Googles and the LinkedIns of the world, et cetera. So we have a diminishing talent pool in general, and I think that has potential implications on broader policy issues such as immigration and so on. But I won't get into that. The other trend that's happening in our industry is that as these technologies become more expensive, the number of suppliers of these technologies is becoming more and more limited. And so 30 years ago, when we had semiconductor companies that had their own fabrication facilities and they could distinguish their products based on their process technology, I don't think that holds true as much today as it used to. So what we have is we've got essentially a leveling of the playing field from a process technology perspective. You can go to foundries and get the process of du jour. In addition to that, the EDA tools have advanced quite a bit, so there's some of those dynamics that are coming to play. So as an industry, obviously, in order for us to prosper, we need to find ways of creating value. And that value usually comes by the process of innovation. In other words, finding new ways of creating that value, whether it's through technology or through business processes. I think both of them are equally important in our industry. And so I think given this landscape, and given that every company is going to have a finite R&D budget for product development or for innovation, I think one of the things that I spend a lot of time on is really, how do I take that finite human capital and how do I enhance the productivity of it, and how do I enhance the innovation capacity of that finite talent pool? And I think this is something that goes beyond engineering. It's something that I think is a very important concept for us within the industry to discuss. Now, from the perspective of technology themes, what we've observed over the last 30 years is that, our company used to provide component-level products. These were things that would go into an 8-pin package, for example, and they used to do a very little tiny function. And now the world has changed. What we're seeing in our customer base is that they don't have enough hardware engineers. So what they're looking for is they're looking for system solutions. They want us, the semiconductor manufacturers, to provide them with as close an approximation to the final system as possible. What that means for us is that we need to have a systems orientation. Our mentality of component orientation has to change, which means that we have to offer higher integration, which is not only analog integration, but also the intelligence that goes with it, the microprocessor, memories, and all that other stuff. And of course, as you go into this higher integration mode, power, especially in mobile applications, is becoming very important. So those are the three themes: the system orientation, the higher integration, and the low power that I see within the mixed signal domain. Now, if you were to look at all the different technologies that are available or that are emerging, You could create a list of about 20 or 30 of these things, but I think each one of them is going to have varying amounts of relevance and importance. But the ones that I picked for this talk are, I believe that there's a lot of opportunity for us to improve the interface that we have with our mobile devices. The human-machine interface, I think, is not only going to be an important factor in mobility, but also in many other applications. So I think the intelligence, the sensors, the processing power, all that stuff is there to enhance that experience. I think sensors are going to become an important part. I think the technologies have evolved to the point where sensors can become a lot more prevalent in systems. Medical electronics is another area. The amount of data consumption is growing exponentially, so high-speed communications, things that go into enabling that high-speed communications for, let's say, macro base stations or for fiber optics or what have you. I think those are going to be continuing to be important applications for us. And then finally, as a broad umbrella, I think, I believe the themes that have been talked about are things like 3D integration. I've broadened that to say it's heterogeneous integration. So it could be the integration of similar stacks of flash, but it could be integration of, CMOS plus indium phosphide, for example, as co-packaging. So I think within our industry, I see innovations in packaging becoming very important.
Much was talked about, Andy, on the Moore's Law, and I'm going to give you sort of a graphical view of where the Moore's Law was and where it's going. So for 5 decades, we simply took bulk CMOS and scaled it initially with aluminum-based interconnects and lately with copper interconnect, and did no other innovation, simply kept shrinking. About a dozen years ago or so, we started changing the device structure from strained silicon to silicon on insulator SOI, et cetera. At the 22 nanometer node, we introduced FinFET, and that's where we are today. But it has been basically silicon CMOS and metallic interconnect. This is all based on classical physics, which is used for modeling and simulation, et cetera. We are at a juncture now where silicon is running out of steam. But silicon will never be replaced by anything. But as Piruz just said, we really will need heterogeneous integration. And there are things like, in the near future, germanium and 3-5 semiconductors will be integrated on silicon. And then the technology to integrate, at least in the near future, will be 3-dimensional integration, as again, Piruz said. Earlier, Andy pointed out a few other problems. For example, power, bandwidth, latency or delay. Power, half of the power on a high-end chip comes from communication and not from transistor. So as we speak, there is lots of research going on to replace or augment metallic copper-based interconnects with optical interconnects. Already for long-haul communication, we use optics, but not on-chip or off-chip. Optics gives us far greater bandwidth than possible. So if we replace off-chip communication by optics, the thousands of pins can be reduced to hundreds of pins. So in my opinion, where are the 2 major recent advances which have taken place? So going from semiconductors, first thing, we are looking at other materials like carbon nanotubes, graphene, 2-dimensional semiconductors like molybdenum sulfide, tungsten selenides. All of them, the scientific community just showed one transistor and said the war is won, done. And the dirty job of engineering was left to engineers. But to my delight, the first carbon-based nanotube computer was demonstrated just about a month ago. So that has totally changed the ballgame. What you will see in the future, more and more work on developing circuits and systems on these new materials, such as carbon nanotube, et cetera. The other thing is in the communication. Optical communication exists, but it's very expensive. unless we develop silicon-based or something which can be integrated monolithically on silicon, optical communication will not take off for on-chip and off-chip. So there, germanium has come to our rescue. Germanium is very much like silicon. Its properties are, it actually gave us 2 Nobel Prizes, that of the transistor and the first integrated circuit. So back to the future. The stumbling block in germanium has been light emission or a laser, but very recent work has shown great progress in light emission from germanium. So going into the directions where new materials and new structures can be integrated on silicon to continue the Moore's law, I think for the next 20, 30 years, we see continuous progress.